Good day, class. In this last part of our forward kinematics graphical user interface calculator, I will teach you first how to add a flash drive or a hard drive in your virtual machine. So from your VirtualBox manager, let's go to settings. Then at the USB, find USB. Choose your USB. So mine is USB 3. Then add your USB here. So the name of my USB is Transcend, or the name of my hard drive is Transcend StoreJet. Okay. Then okay, so you can just do this, or you can do this only if your virtual machine is off. So you cannot do this if your virtual machine, your Ubuntu OS is running. So my Ubuntu OS is closed or turned off, so I can add my hard disk or my USB in my virtual machine. So let's start the Ubuntu OS. So the reason why I teaching how to add the hard disk is because, or the USB is because we will capture an image from my hard disk that will be displayed in our graphical user interface. Oh, sorry. Okay, let's go back to our Visual Studio Code to add our image. So the image format or the image file you can only add to your graphical user interface is in a PNG format or in GIF format. Okay, so at the line 217, after the label of the unit of our z-axis and before our mygui.main loop, we will add our photo image code, or the code that will let us display our image in the graphical user interface. So let's name this image, sorry, display image, display image X. So let's name our image widget img. Oh no, it's not a widget, just a variable img for the capture of our image from the hard disks. So let's see if the hard disk is inside our virtual machine. Okay, it's in here. Scara v3.png. Okay, from our Visual Studio Code, type command photo image, close open parenthesis, then inside is the file. Okay, so the file should be in our TKinter folder. So let's copy this Scara v3.png in our TKinter folder inside the Scara v3 folder. Okay, scarlet v3.png. The name is scarlet v3.png. If your png file or if your .png is in capitals, you should copy it. If it is in lowercase, you also need to copy it. Mine is in uppercase, so it is it's all capital letters. Okay, .png. Next, we will create the widget variable, which is a pi. Then the command label, so open parentheses, our main, our graphical user interface main variable, which is my GUI, then command image and our variable eing. Then we will position it inside our graphical user interface. We will use the .grid command. Okay, so it is the last part of our graphical user interface design. So we will put it in row 3, column 0. Okay, row 3, column 0, then Control S. So let's see in our terminal what this looks like. So we will go first to our star v3 folder, then to our TKinter folder, and we will run our mygui.py. So Python 3 mygui.py. Enter. Okay, so now our image is inside our graphical user interface. We can also change the size of our image if you don't like this size. Okay, let's go back to our code. Okay, it is advisable to change the size of your image from your Windows. Okay, from your Windows OS in Paint. Okay, instead of coding it in Python. Okay, so using the image that subsample, okay, you can change the size of your image inside your graphical user interface. Okay, so this will be the size. I think this is the height and the width. If this is the height and the width. Okay. Okay. So I think this is the height and the width. So you may play the size of your image inside your graphical user interface. Okay. So next is checking if what you are calculating in your design calculator is correct. Okay. So let's test again. We will test again values in our link lengths and joint variables. So this is in centimeters. Okay. So let's check first if the joint variables are 0. Okay. So forward button, so this is the position vectors 30, 0, 25. Now, how to check it? First, you may split horizontally or split vertically this terminal. Then, let's go back to our v3 folder. Then go to Kinematics folder. Okay, inside the Kinematics folder, we will run the FKin.py. So our FKin.py will require us to input the value for our link lengths, but this is in millimeter. So to match it with the values of our graphical user interface, we will just add 0. Okay. So the value of our graphical user interface is 10 centimeter, 15 centimeter, 15 centimeter, and 15 centimeter. So this will be 100. Next one, 50, 50, 150. And next is the joint variables. D1 is in a, let's make this 0 first. D2 is 0. D3 is 0. Okay, then enter. So this will show our homogeneous transformation matrix. And third column, the fourth column, if you are not familiar with Python programming, if in Python programming you will start your count from 0. So this is row 3 in Python programming. Okay. So at row 3 or row 4, x is 30 centimeters. In our homogeneous transformation matrix, this is 300 millimeter. In y-axis, this is 0, but 0. The z-axis is 25 centimeter. In our homogeneous transformation matrix, it is 250 millimeters. Okay. So this is if the joint variables are all 0. So let's compute it if it is not 0. Okay. So D1, let's check if D1 is 5. T2 is negative 90 degrees. T3 is 30 degrees. So forward. Okay. So let's hide our plot. Okay. So our x 7.5 centimeter, our y is negative 27.99 centimeter, and our z is 30 centimeter. So let's check it in our FKin.py. Okay, A1 again is 100, A2 is 150, A3 is 150, A4 is 150. Now our D1 is 5 centimeters, so this is 50 millimeters. Our T2 is negative 90 degrees. Then T3 is 30 degrees. Okay, so let's check. They have the same answers. So this is our homogeneous transformation matrix. Okay, the x is 75 millimeters, so the same with our x here in position vector. The y is negative 279.904 millimeters, so the same with our y-axis in our graphical user interface. Then the z is 300 millimeters, the same with z is equals to 30 centimeter here. in our graphical user interface. So it is the first way you can check if your calculator is correct. The another way is using MATLAB. Okay? Using MATLAB because the design of our calculator is also based in the robotics toolbox by Peter Corke here in MATLAB. Okay? So to check this, let's match the values of the link lengths and joint variables in our MATLAB. So A1 is 10. Unlike the robotic toolbox in Python, the robotic toolbox in MATLAB has no unit. So we don't need to convert this. Okay, so to check the computation of our forward kinematics. Wait. Oh yes. So to check the computation of our forward kinematics, we need this syntax. Okay. So a variable, I will name it fk. Then it will be equals to the variable of the robot. Then the command is .fkin or fkin close open parenthesis. Inside the close open parenthesis is the joint variables. Okay? Or the joint variable. Because I put the joint variables inside another variable which is af. Okay? Inside af, this is an array. Okay, an array of variables. So let's test the 5, negative 90, and 30. So this is oh, refresh. Okay. So the joint variables are 5, negative 90 degrees. So in MATLAB, it is negative pi over 2. Then 30 degrees. So in MATLAB, it is pi over 6. Okay. So inside the variable AF, the joint variables, and I will use the variable AF inside the FKin or FKin command. Okay. So this will show also the homogeneous transformation matrix of this Cara G3 manipulator. Okay, let's run this program. Okay, so because this is MATLAB, so this will also show the model of our manipulator, but the model is not properly scaled. Let's close the figure. And let's look at the homogeneous transformation matrix. Okay, so this is the homogeneous transformation matrix. What we need here is the position vectors. So at x, it is 7.5 centimeter. So in our calculator, it is also 7.5 centimeter. In Y, it is negative 27.99 centimeter or negative 27.99. In our graphical user interface, it is negative 27.99 centimeter. And at Z, it is 30 centimeter. So also in our graphical user interface, it is 30. So this is 30 centimeter. Okay, so our calculator, our design calculator is correct. Okay, so this is the lecture of how to create a mechanical manipulators forward kinematics graphical user interface calculator.